Person, I like being here to learn.
That's right.
Just listening to it, I really don't pay attention.
And I think that, yeah, it's kind of a hand-holding thing. Some people could do it responsibly, but then more often than not, it's not done responsibly. So, okay, should we do this? Keep going. I will say, and I will admit this now, I do have a YouTube page where I am posting all of the recorded lectures. Okay, I was going to keep it a secret because it's for Neil, because Neil has practice until 10. And then he comes in late every day, and then I was like, I set this up for Neil, and I was like, oh, I'm just gonna keep it. Because I ran into a problem is I recorded all my lectures and structures one last semester. When I had you guys in structures one, you came to class and you did it responsibly, but structures one last semester, it was like half the people there at all times. The rest of the people just were like, screw this, I'm not coming. And so I was like, fine, I'm not ever doing this again. I mean, I'll do it for dynamics, but now I have this, anyways, this is the long story. But I will put it on the thing. But you guys got to keep coming to class. But that happens where, like, Kira, for instance, is not here today. She had an appointment, so she's like, "Oh, can you record class for me?" I was like, "Fine, that's fine." Right? And then sometimes you have legitimate reasons for not being here, and so just keep coming to class. Maybe I'll make a wheel. I'll make a wheel for you guys too, right? An attendance wheel that we could go, and so that it'll give you the incentive to come to class, right? Because it's better, because then we can actually have conversations. Soonish, we're going to put together a tour, right? We just do that every once in a while, just for the heck of it. I think what we're aiming for right now is that building downtown. It's a podium structure. They have the timber that's being, put on top right now. It's starting to go up. So sometime in the next couple weeks, we'll probably go to it. What?
Which one?
It's right next to the other new one.
The IMEG one?
The IMEG one, yeah.
The apartment complexes?
Right next to the apartment complex is the hotel. Yeah, the hotel right next to the apartment complex. And then I think also SIP panels, like that factory kind of needs to go to. And then, Andrew, you had something? What do you got?
Yeah, I'll do later in October, there's a steel building going up on Main Street in that big empty lot next to the National Bank building.
Okay, yeah, pretty cool. Just because it's good to kind of go out and see the stuff. And we didn't come up with a time. I think it's going to be on a Tuesday or a Thursday. And I know, like, you worker people and you can't do it, but maybe you could if it's interesting enough. I understand that you're actually doing the work and you can tour. I get it. But I think that's otherwise I don't think it will be able to get any time to work. And if it works that you could sneak away for an hour, that'd be awesome. So, okay. So what we covered last time, quick little refresher. Okay. So basically we derived the equation. Right? This is the equation that we're going to use, right? It's the pre-stressing force divided by the area of concrete minus the FPEP over the S, and it's S1 or 2 because it depends on if I'm going to go to the top or the bottom with my calculations. And then the external moment and again, S1 or S2, depending on if I'm going up top or bottom, right? So this is the portion associated with the pre-compression from our pre-stressing. This is the moment, the internal moment caused by the eccentric pre-stressing tendon, right? And then this is the cause of the external moment, right? And that's it. That's the only one equation that we need to use. And like I said before, like those mechanics are really simple, but where it gets complicated when we do our designs are one, what do we use for FP, right? It depends on which load stage we're in, right? If we're in the initial load stage, right, when we transfer the loads from the pre-stressing into the concrete or when we post-tension the member, this is not going to have pre-stress losses in it, right? So it's going to be the full pre-stressing force. Later on, when we have, when we're looking at 28 days out or beyond, 5 years actually is what we designed for, we're going to use a different FP. We're going to use the effective pre-stressing force that accounts for any pre-stress losses that happen. Okay, so these FPs are going to be, depending on which load stage we're looking at, they're going to be different. The other thing that's going to change that we're going to talk about today is EP. Right? Sometimes this EP isn't constant, right? The way we've done it so far, we've drawn it as being constant, like a constant eccentricity, but there's different shapes of these things as well, right? So you could have a drape profile or harp profile, and so EP is going to be changing as a function of position, right? And then our external moment, that also is going to be changing as a function of the position along the length of our member. So really, this we're going to use a couple different values for this, a couple different values for this. This can change as a function of x. This could change as a function of x, and we have the top versus the bottom. So that's where things get a little bit complicated. The other thing that adds complexity to this is what do we use for, what are we comparing this to? What are we comparing these stresses to? What we're comparing them to is allowable stresses that ACI prescribes, or whatever your code, whatever building code you're looking at, it prescribes, right? And so if I'm looking at compression at the initial stage, that's going to be FCI. That's going to be defined by ACI. FTI, what is the allowable tension stresses, at the top or bottom, depending on how this thing is oriented, and if it's simply support or whatnot. This is my allowable stress during service loads, and this is my allowable stress, tension stress during service loads. Okay, and so at every location under both these loading conditions, the initial and the service cases, we have to make sure that our calculated stresses that come from this equation right here are more than this FCI and less than the FTI. And this, by the way, this whole thing takes into consideration that this FCI goes in as a negative number, right? This is sticking to our sign convention. So this would go in as a negative number, this would go in as a positive number, and then our stress has to be between that negative and positive number. And same thing here, okay? And so it's the same limits. These are written exactly the same, but what will control, you could apply a little bit of logic, right? In a case where this thing is popping up under the initial transfer, what's gonna matter is up at the top, it's the tension up at the top and the compression down at the bottom, because this thing is curved down, so the compression down at the bottom, right? Say under service conditions, again, these are written exactly the same, but what would control under a standard case would be compression at the top and tension down at the bottom, okay? That's it. You always just have to make sure we're within those stresses, right? And like I said, it gets a little more complicated by all the other stuff that's floating around. All right, so then we went in and said, well, what are those things? So we looked at, the jacking pre-stressing forces. This is essential to the tendons. These are the most stresses that the tendons are going to see when we load them up. Then we went in and looked at classification. We're going to deal in this uncracked case. Depending on your classification, which is based off of your tension stress in your under service conditions, it's based off of that. As long as it's less than 7.5 square root of F prime C, we call it uncracked. When it's uncracked, it tells you how to go about analyzing it, and then we're going to stay away from the class T and the class C, right? And then we went through and defined what FCI is, right? We're going to stay away from the ends. We're just going to do kind of all other locations. That's the 0.6 F prime CI, but we know that near the ends, we can go a little bit higher. It might be okay. FTI is, again, we're going to do all other locations, but no, we have a little bit higher limit when we go out there. So it actually defines these FTI and FCI, and they're both based off of F prime C. And now F prime CI even. It's the initial it's the initial concrete compression strength that we expect to do the transfer at, the initial, right? And that would be something that would be given to you. F prime CI would be given to you in the problem statement. Then you would just make sure you stay less than 60% of that at the beginning. And then you would calculate this 3 squared F prime CI to determine what FTI is. And then again, when you see the square roots, that FCI has to go in PSI. You gotta be careful of that. All right, FCS, 2 different limits for the FCSs, depending on if you have sustained load or not. We have a lower limit for the sustained load because of creep. We have a higher limit when we take into consideration the total load, because that includes the live loads that come and go and aren't there constantly. Okay, cool. So those are those allowable stresses. So we just need to make sure we stay within those limits. So I'll show you, we're going to dive into actually analyzing one of these in a second. Okay, so we have basic strand patterns, straight, or standard, just as a constant EP. What up, Neil?
Mike.
How you doing? Right? Oh, I'm so mad about that. Right? Constant EP to go that. Draped. Like that. And I think we're going to estimate that as like a parabolic shape, like in a lot of equations. It's not really a parabola. It's a funicular shape. It's the shape that a cable would take if you draped it between 2 points. You just let it sag as it goes there. It's not a parabola, but it's close enough. Some nerding out there a little bit. Funicular. No, nobody else. Nobody's excited about that. Right? This obviously is post-tensioning. It's just important to note that you couldn't make this shape with pre-tensioning, right? Pre-tensioning, you stretch it first, and then you cast the concrete and then go. You can't stretch, right, a cable into a curve, right? I mean, you could try, right? You could put a bunch of tie downs along the length of this thing, but still it would be straight lines in between each one of those things the way you do it. So this would be a post-tensioning, right? And then we have harped is the last one. Right? And there's a couple different harping methods. Like this. You know. Right? And you can also do it where you just have one harping point, like right in the middle. You have a couple different depression points is what those would be called, where you hold it down. And that you could do, right? You can imagine doing that in a pre-stressed plant, right? Before you cast the concrete, you just put some big tie downs right here, right? And then you pull this sucker, right? But imagine the forces that you're going to be getting at this location right here. There's massive forces when you do that. When you're pulling on this thing, millions of pounds in this direction, this thing's going to want to shoot up, and so you have to hold it down, right? And like I said, we've toured there's a pre-stressing plant in Billings. We've toured that a few times. And the people at the pre-stressing plant is like, they don't like it because it's really scary. Right? You can imagine, right? Millions of pounds and a million of pounds, right? And if this anchor fails and this thing shoots up and chops people's heads off and stuff. I don't know if it actually ever has chopped their head off, but I wouldn't want to be the first. You wouldn't want to be the first. We've talked about this. I was a big TikToker for years, right? And then it was too good, and it really sucked me in, right? Like I was just like, oh my God, this is too engaging, and I had to quit it. I had to quit my TikTok. And the algorithm was bringing me towards like, oh, this extreme political. I hated it, right? And so I was just like, oh my God. And so I was like, I'm off, and I switched over to Instagram Reels because they suck, right? I forget where the fuck I was going with this. I really do. I really forget.
Probably some real estate getting chopped off.
Oh, that's right. That's okay. Thank you. That's exactly right. And so they suck. But then immediately, I started getting some of the craziest shit on my Instagram Reels, where people were like getting their heads chopped off, or they're crashes,
Yeah.
right? Lots of like
Shootings. You just watch people get shot on the sidewalk.
Yeah, get shot on the sidewalk and stuff, and they're like going off big ramps, and then just wrecking terribly, and just like, what the fuck, right? And I had to keep saying, I don't like this, I don't like this, I don't like this. Now finally, the algorithm is gotten to a point where I don't get those like death shots anymore. But I mean, I was like, shouldn't this be illegal? Like, am I supposed to be seeing people die all the time? I got this one page that was like, it would show an accident. Well, I mean, I went and looked, right? Because I got the reel and then I went and looked, and maybe that's why I kept getting them, is because I kept engaging in them. But it would show a fatal accident, and then right before the fatality happened, it would cut away, right? Like you would see it happening, but they don't actually show it. I was disturbed for so long. seeing those ones, right? There's one where like a guy, like he was dealing with, he had these tires, these big wheels and tires, like big huge ones on top of his trailer, and he was like overdoing something with it, and it fell off, and it like swung around and squished him, and then but it cuts away right before that happens. So it was like, oh my God, and then what's the next one look like? And then it just kept going. That was too engaging. But then now, part of the reason why my algorithm has been corrupted, it's been helping. I got rid of that stuff. Is because my wife constantly sends me reels, and her reels suck. They're they're terrible. But then they corrupt my algorithm. But they're also very wholesome, and it's just like. I'll give you an example someday. I'll find one that she sends me, and then my kids will not open reels from their mom because they don't want their algorithm to get corrupted by their mom's like junk stuff. But I take it for the family, and I look at it anyway. It's like, all right, here we go. That's funny. That's a good one.
I'm gonna send this recording to her.
He knows. He knows. We do. This is literally how we interacted in the evening. She's laying in bed and I'm laying in bed, and we're just sending each other reels like nonstop, just reel to reel, just back and forth. Mine are good reels. Those are bad reels. Yeah, we had a term for that. I forget what it was. All right, so just to right, our equation is this: F. Why are we doing this? Right? Why are we doing this? This is FP over AC. This is minus FP EP all over S, and then we're adding on it M external over S. Right? And I mentioned this before. What we're doing is we want these to cancel out. Right? Because again, what I want, right, is I want this, right? I want the pre-compression force, right? But ideally, if you could do this perfect, I want my external moment and my internal moment to cancel out, so that I'm just canceling out the effect of the external moment. Because if I do that, then I'm not going to get any tension. The only thing that's left is compression along the whole thing, the whole cross section, right? Well, what does our external moment look like? Well, our external moment actually looks like this, right? Under standard simply supported thing, right? It's a parabola that goes this way, right? And so if I make my tendon go like this EP, will basically, it'll make it so that those two cancel each other out. My external moment, my internal moment cancels out. If you're doing pre-tensioning, right, I can't make this shape, but I can do this, right? I can make it be more eccentric where I need it more eccentric and less eccentric where I need it less eccentric, right? And we get these two things to cancel out. And that's great, right? I want to cancel out. I mean, this will do it. This we put it down at the extreme location right there, and then this is going to do it. This would, where it counted the most, my internal moment and external moment would cancel each other out. Where you actually can run into problems is near the ends over here, because over here there isn't any external moment, or the external moment is really small. But I have this pre-stressing tendon out there that's saying we're trying to cancel these things out. Well, if this goes to zero and this still exists, I can run into some problems, right? I can run into problems where I'm getting cracking up at the top at the ends, because I don't have the external moment to cancel it out. I don't have, right, my moments shaped like this. I have no moments at the ends. If I don't have any moments at the ends, and I have this big pre-stressing force saying you need to pop up, I could get cracks at the top near the ends. Near the middle's fine, but near the ends I could run into some problems. And there's some ways, and so to avoid that, right, we just have that thing change. Have it have no eccentricity at the ends, and then have a major eccentricity in the middle, right? And that's what we do. Okay. I think a lot of times, though, they do get designed as straight just because it's easier, right? If you're making these things in a pre-stressing plant, just make it straight. What they do in post-tension floors, right? Remember I said that the ducts and the pre-stressing tendon are kind of one unit. And what they do is they lay it out on a floor, like on the floor, and sometimes it's going over a bunch of beams, and so sometimes you want positive, sometimes you want negative, and they just literally just lay it out and they just drape it as they go across, and they come back and cast concrete around it. In 1 second, I'm gonna show you. Maybe I'll show you. I can't get that. Yeah, see the, yeah. Oh yeah, look at that. Just Axel, you remember Axel? All the way from last semester? See, what's crazy though, right, is I say that, and those of you that had classes with Axel, you know Axel. Those of you that didn't have classes with Axel, like some of you, Paige, you know who Axel is? See? It's how quickly you get forgotten around here, right? I'm serious. That's really strange. Like, we've had professors here. Ted Lang was a professor here for 50 years. You guys don't even know who the fuck Ted Lang is, right? And he was forgotten within the first years. Everybody's like, I don't know who Ted Lang is, because you guys are always changing, right? But Axel Tanner, those of you that do know Axel Tanner, he was on a job site. This is up at Big Sky. This is Big Sky Town Center. They're doing a post-tension floor. And these are pre-stressing tendons. Inside of this, there's a piece of plastic right here. This is the duct work for the post-tensioning. And then inside of that is a post-tension strand, right? And each one of those things. And so they lay these things out, right? And they go, right? So near the middle, they want it near the bottom, and this is going over a column line, and so it's gonna be negative moments when it goes over there, so then they move it up to the top, and then across the middle, they bring it back down, and they move it back up to the top. And then over here, there's something blocking it from going straight, so they actually do a lateral sweep on it off to the side. And so they're gonna cut, and then there's, we're gonna learn about this later, but these ones are all banded in one location, and then in the other direction, they're distributed widely. There's some reasons they do that, but we'll learn about that later. But you can see a bunch of post-tensioning tendons going this way and a bunch going this direction. And so that afterwards, they're gonna cast the concrete on this, and then they're gonna come back and then they're gonna load up each one of these things after the concrete's come to strength. So they're doing it in Montana. All right. Relevant. What we do is relevant. That was my establishing. This happens, right? So they're going up and down as you go along. And so that, by the way, the moving them up and down is still doing this, right? Because what's happening is, right, my external moment is going positive, negative, right? And so my EP is going to go below in some cases, above in others, below in some places, and above in others as it goes across. Okay. So how do we analyze these things? There's a couple different methods here. We're going to just briefly talk about it. We're going to focus mainly on this guy. This is just analysis. This isn't design at this point. This is just analysis. We're going to do direct determination. Right? That's actually what we're going to do. We'll talk a little bit about the other ones here too, but just to lay them out that they do exist. Use equations from above to calc stresses along length. Different load stages. It ends up with quite a few lines for this, but we use equations above to calculate stresses top and bottom along the length for different load stages, right? And you can imagine this is going to be a plot of stresses, right? And they're going to be a function of x. We're going to do this in a minute. I just wanted to some foreshadowing. Because they're changing along the length, and so they're going to have that, okay? Equivalent load procedure, right? We're going to say that this is used in post-tension floor design. PT. And they'll say explain more later. Right. What that does, as the name implies, is it comes in to this, right? And it starts talking about what could be an equivalent load that would give me these same moments, right? An external load. You pretend that there's some external load. So when you analyze it, you just add in this extra component, like another distributed load. It's not really there, but it's a distributed load that's acting in the opposite direction. So it would be, for this case right here, we could say, well, this pre-stressing is going to cause, right, it's going to cause a parabolic moment, internal moment. So you would come in and say, oh, let's just pretend that that's a force, a distributed force that with an upward magnitude that would cause that same thing. And there's some reasons for doing it. We're going to get into more detail later, but it has to do with trying to analyze things with finite element analysis. You can't really analyze. Finite element analysis doesn't know how to handle a pre-stressed member. It does know how to handle external loads. And so what we do when we do this finite element analysis is we pretend that there's just an internal load that causes the same moments that this thing would cause, and we go from there. Getting ahead of ourselves, okay? And then there's also this last one. This used to get used a lot, the C-line method. And a few years ago, people thought it was really funny because they kept thinking I was saying sea lion, like a sea lion method. So now I say sea lion on purpose. Right? The sea lion method. What's the difference between a sea lion and a seal?
Ears.
They're different animals.
Well, I know, Anika. I know they're different animals, but when I look at them and I see it swimming in the water, I'm always like, oh, look at the seal, and somebody's like, that's a sea lion. Like, how am I supposed to know this?
You know, look at their slippers.
They what?
Sea lions have much stronger flippers.
Was I gonna have bench press for me? That's good. That's good, Thomas. Thank you. Anika, you're from a place that has Alaska. You see these things? Everybody, what am I looking for? The ears?
Ears.
What about the ears?
One has internal and one has external.
Huh.
And then also sea lions have like long flippers and seals have like short ones.
I noticed a little condescending tone to your voice there, Anika. Right? I
You're asking the difference between a dog and a cat.
Shit! Oh man, shots fired! Oh God.
I thought you were setting up like a pun.
No, I'm really curious. I want to know. I mean, I look at him just like, oh, look, it's a seal. And then it's a sea lion, dumbass. And then like, Anika probably is the one yelling at it, right? I mean, it's funny because I do the same thing. Like when they go to Yellowstone, everybody's like, oh, look at the wolf. There's a wolf, and it's clearly a coyote, right? Like it's clearly a coyote, and yet they're freaking out about it being a wolf, right? I mean, it's so then I'll pass judgment on that, but you don't pass judgment on me, Anika, all right? Same thing with a llama versus an alpaca. You guys know the difference between those? They're different animals. I know this. But do you know? Like, could you look at it? If I put them both up there, you'd be, that's a lie, Neil.
Oh yeah.
How?
I look at the alpacas all the time over there by Granny's Donuts.
Yeah, but how does it look different
Seen
than,
the hump on a camel's back?
not a camel. I'm not a camel. A llama.
A llama and a...
Yeah, I know the difference between a camel. I know the difference. I know the difference between a camel and an alpaca, but I'm not sure a llama and an alpaca. So you don't know the difference,
They
though.
have different feet. I'm pretty
Also, a
sure.
llama's bigger than an alpaca.
That's Chad.
Maybe this is it. Maybe next time I'm gonna set up a little quiz for you guys. Maybe that'll be on the exam. There'll be a picture of a sea lion and a picture of a seal, and you have to identify which is which.
How do we trust that your
I don't
key is
think
right?
Yeah, AI. And then we'll do the same thing with llamas and alpacas and see if you can see the difference. This is a good, yeah, thank you. That'll be on the exam.
Is that extra credit? Is what's the difference between a llama and a...
There'll be pictures. There'll be pictures. Maybe it'll be like a picture of I got it. A llama, a seal, a sea lion, and an alpaca. And then you have to match. You have to match which one it is with. And a camel. I'll throw a camel in there too, Neil. Wolf and a coyote. A wolf and a coyote.
Bison and a buffalo.
What's that?
Bison and a buffalo.
They're the same, aren't they? Just oh. Well, but we call them. We use them.
Yeah, but we're wrong.
Yeah, but we're wrong. A bison and a buffalo. A black bear and a grizzly.
That's the hardest one.
That's a hard one. Yeah.
You should make it
Black
black
bear.
and white too.
You
What's
should
that?
do it, cinnamon-
Black and white for the.
Oh, black and white. What's that, Anika?
Cinnamon bear and a brown bear.
Yeah.
Grizzly would-
Yeah, grizzly. Yeah. Oh yeah, this would be a great exam. It's gonna take a most one pre-stress problem, a lot of animals. Okay, so back to the sea lion method. Okay, we're not going to use a sea lion method, but what I like about it is when the discussion leading up to it, like how the difference between regular reinforced concrete and pre-stressed concrete. And this, they used to analyze these pre-stressed beams this way. We don't do it anymore. And the reason we don't do this anymore is because we have like computers and we can do plots of Excel plots really easy or MATLAB plots of stresses, and it's super easy just to do the regular method. But back in the day when they didn't have those tools, they came with other ways to picture what's happening. So what we're going to do is we're going to compare reinforced concrete to pre-stressed concrete. That's the PSC. Okay, so and then we're going to look at no load, and then we're going to add some load to it. So with no load at all, what are the stresses in the reinforced concrete beam? Nothing, right? It's just sitting there. It's passive, right? A concrete, I mean, obviously there's self-weight and stuff like that, but we're just without any load, no self-weight. So if you just put it in a concrete beam and I set it on this table, completely supported along the length, it just sits there. It's nothing, right? Nothing happens to it until I add load. Whereas a pre-stressed concrete beam, that's not the case because they're preloaded, right? So it has some stresses to begin with, right? And so we have, we got FP, right? We're pulling on that pre-stressing force like that. And then we have equal and opposite is going to be FC, right? The resultant compression forces are going to be like that, right? And we've got the CGC in here. CGC floating around right there. All right, and this distance right here is what we're calling EP. Dash line. My eccentric pre-stressing force, right? And this guy right here is what we call EC, right? If we were to calculate, right? If I took this thing and I stretched steel down at the bottom and I cast concrete around it and released it, and there'd be this pre-stressing force that would, this massive pre-stressing force, that's causing this. Oh gosh, hold on. Yeah, massive pre-stressing force. FC and FP have to be equal to each other, right? FP has to be equal to FC. Right? Because it has to be in equilibrium, right? The system has to be in equilibrium. So FP and FC are equal and opposite to each other. Should I yell at him? What's that?
Llamas and alpacas look pretty different.
Yeah, but that one has a haircut and the other one doesn't.
Pretty standard. Like the ears.
The ears? All right. Alpaca versus a llama. Versus a camel.
For anyone here that doesn't watch the recording, they're going to be so confused.
I know, right? We on the exam, that's right. Kira, let's keep it a secret and see. See, every time I make fun of this camel thing, I look at Neil and I actually get a little nervous. So Neil, I apologize. No hard feelings. Right. Don't beat me up. Okay, so EC, EP, these things are lined up. The whole point is they line up. They're right up next to each other, right? They have to be. There's no external moment. If FC didn't line up with it, it was up here, there'd be a moment, right? And this point right here, there's no external moment that's applied to it. Okay. And then, so that's FP is equal to FC, and then also EP is equal to EC. the eccentricity of both of those things. If I was to find the central location of this, right? And by the EC there, let me add that to it too, right? It would have stresses that would look like this, right? And you could figure out, right? You'd have stresses that are doing this, right? Acted this way. I could find out where, where the resultant from these stresses would be. And that resultant from those stresses would be lined up directly with that FP. It would have to be lined up directly with that FP. Okay. But then if I apply load, so that's what happens when we have no load. When we apply a load, right, as our load goes up, right? In regular reinforced concrete, what we get is this. Down here at the bottom, we get T, right? And now I'm going to get a compression force up at the top two. Right? C and T. In this case right here, C is equal to T. That's kind of fundamentally what we do in regular reinforced concrete. But then the other thing that's happening, though, as load increases, magnitude of forces increase. How did I italicize that? But stay in same location. Okay. So to resist the load when you apply moment to the reinforced concrete, to resist the moments that are applied to it, C always has to be equal to T because there's no other forces happening there, right? And then the moment comes from C and T getting bigger. C gets bigger, T gets bigger, right? Up until when it yields, right? And then T kind of gets flattened out and C gets flattened out. But generally speaking, they stay in the same location and they're the same magnitudes. Or sorry, the magnitudes increase as we apply the load. With pre-stressed concrete, it's different. Same thing that are applied here. My FP is going to be down here. The pre-stressing force is going like that. And then we got my CGC going down the middle again. My EP, this is fixed, right? My EP is fixed. EP. Right, or it can be changing in height, but it doesn't change as we apply load. But then what does change is now my C will move. My FC will move. Right. My EC changes then. That is EC, right, as the load applies. Right? So what happens is it starts out like this, right? It starts out where they're lined up like this, but as you apply load, then that FC moves, right? Because it has to resist that, we have to resist that moment, and we do so with EC and EC becoming eccentric, right? So in this case, just going to summarize some stuff here. Again, FP is equal to FC, always has to be equal to FC, or negative, I guess there is a negative floating around, but equal and opposite. No, I guess it's just like that. But what doesn't change, we said before, magnitude of forces, not foxes, stay same, but location of FC changes. EC changes. Okay, so that's the difference, right? Instead on the left-hand side, C and T stay in the same location, but they get bigger. On the right-hand side, FP and FC stay the same, but the location of FC changes, right? And the reason this one, right? The reason we say this doesn't, I mean, does FP actually change? Yeah, it does actually change, but not that much. Remember, one of our assumptions was that the applied moment doesn't cause a change in it, right? And so you can actually calculate what that EC is. So you could do this. If you said M external is equal to FP times EP minus EC. Right? So if I wanted to figure out the moment that's caused by FC and FP, I mean, it's either FP or FC, you could do it, but it'd be that times the distance in between them. Right? And the way that we have our naming scheme with positive, negative, this is what the equation is that you actually would use, right? And so if I wanted to calculate where EC was, I could do that. I just use that equation right there. I say EC is equal to EP minus M external divided by FP. Right? And so I could calculate what EC is. And I could actually plot EC along the length. And that's what they used to do when they did this evaluation, is they would calculate what EC was and then plot it along the length. Okay? One of the reasons why, oh yeah, I can say that, plot this. EC, or the C line, that's what they used to do. Plot EC or C line along the length of the beam and compare it to limits. That's why it's called the C line method, is because we plot where the C is at, right? One thing that I want to note about doing it this way that's actually pretty interesting is where this FC acts. And otherwise we would never talk about this, but what's really weird to think about is that a pre-stressing member, and this happens sometimes, if you cast a pre-stressing member and then let it sit in a yard for too long, what'll happen is it'll creep, but it'll creep in a way, which is really weird, it'll creep up. Isn't that weird to think about? Right? You say, I'm going to cast this pre-stressing beam, and they put it in my yard. It doesn't get put into application where it starts getting all the loads. It just sits in a yard for a year, or a year or two or three, and they want to go use it later, but they can't use it because it's creeped up. Right? And what it is you've designed it to have these loads on it, and the loads aren't there, and so it pops up and it'll creep up. Right? And that can happen in service too, where you put it in service and then you'll get the creeping again, right? As the concrete that's in compression will squish too much, and then it can pop up on us. Right? And what's going to depend, but then also it could creep down, right? If you put enough loads on it, it'll creep down, right? If the compression force is in a location, you're going to get the creep where it shrinks, and then it'll creep down with time, which is more how you would think of it as opposed to creeping up. And what defines if it's going to creep up or creep down is dependent upon where FC is at, right? If FC is below the neutral axis, right? If my FC is down here, which way is it going to creep? If my FC is down here, up. It's going to creep up, right? Because you're going to get shortening, right? The bottom here is going to get shortening, right? And so it's going to creep up. If my FC is above the neutral axis, then it's going to creep down, right? That's just a different. I mean, this is the one place where we see it at play here, is where this FC is, right? And we can make note of that, right? If FC is above C, G, C, creeps down. If FC is below C, G, C, creeps up. So Kira, I would highly recommend watching the video because we had a very intriguing conversation earlier about what might be on the exam when we have it. And I'm going to tell everybody what the secret... Neil, I'm telling everybody where the YouTube page is.
Oh, I thought it was our thing.
It was our thing. It was our thing. But word got out that it existed. Gavin knew that it existed. And then Kira wanted me to record today because she had an appointment. But I am going to open it, but everybody's got to keep coming to class. I'm going to create a wheel. I'm going to do it every day. We're going to do it. Just see who's here. Just because it's fun. You don't like that, Connor? I'm gonna put Connor's name on it twice because he doesn't like it. He's gonna do his name on there 2 times.
Now I'm gonna skip out a spite.
Yeah. Today it was funny because I did the drawing, right? I did the drawing in Dynamics. I dropped 3 names. And then afterwards, the kid came up and was just like, hey, dude, I came in 3 minutes late. I'm so sorry. Like, please give me the credit for it. And they had all these things, and I didn't even call his name. His buddies were fucking with him because he came in 3 minutes late. And his buddy said, hey, dude, they just called your name. You just missed it, right? And then so afterwards he came, and they let him come up to me and argue for. I was like, dude, I think they're fucking with you because I did not actually call your name. It's funny. It's a good joke. Go ahead and use that one. Okay. 4 minutes. All right. So kerns. I hate them. We're going to briefly talk about them just because 1, they get used in other areas. 2, you may hear kerns at some point related to pre-stressed concrete. If you ever go into it, it might be. You've heard kern before, is that correct?
No.
Kira has? Where'd you hear it, Kira?
In the textbook that you assigned.
Oh, shit. Yeah, you read. Look at you, nerd. Right? But that's part of the reason why I want to do it is because Stanton loves the kerns. And then, yep, and so we're going to talk about the kerns. And they're a property of the beam. Thomas, where'd you hear of kerns?
Center third of cantilever retaining wall.
Oh, really? No. What was that?
Concrete.
I bet it's related to the same thing.
Yeah, so there's no tension.
That's right. It's tied to no tension. It has to do with a case where there is no tension. It also shows up in geotech, right? There's a discussion of kern somewhere in geotech, right? Right, Anika? Right? Yeah. And so we're gonna do it here. That's all. We're just gonna, because they get used as Stanton's notes, and whenever they gets used, it is associated with tension. We will define them here. And what Stanton ends up doing, here's our beautiful equation that's beautiful, right, for calculating what these stresses are. He comes in and says, oh, by the way, we can slip in this definition of a kern, and then this equation can be simplified down to this equation. And I was like, well, no, I don't like it. I don't like doing it, right? Because I don't know why he did it, or why he does. I mean, it's just because it happens in other texts and stuff. This one's beautiful because I know this is the concentric, this is the eccentric effect, that's the external load. It's beautiful. Like, you know what each, and then this is like, I don't know what the fuck any of this is, right? And so we lose that. But anyways, we'll discuss what a kern is next time. Right, we got 2 minutes. Yeah, that we'll call it there, and then we'll come in and talk about design, and then build ourselves up to this, which is your next homework assignment. So, which is basically making these exact plots. So, you can do it in Excel. This is one where you could do either one. Yeah, I mean,
Could Chat do it in that way?
Chat could do it in MATLAB. I'm certain.